Welcome. We are looking at section 6.2, and today we are in day 2 of this section. We will look at conditional probability and Bernoulli trials. Conditional probability. All right, so the probability of event 2 given event 1 is the probability that event 2 will occur if event 1 is known to have occurred. And it has this notation, and I read this as the probability of E2 given E1. So if I'm thinking about this as a sequence of events, it's a little bit in reverse sequence, because I imagine that E1 has occurred, and now I want to know the probability of E2. Here's an example. Draw 2 cards from a deck without replacement, so maybe you draw 1 card, place it on the table, and then draw a second card. Event 1, the first card is a king. Event 2, the second card is a king. So what's the probability of event 1? You just draw 1 card. What's the probability that it's a king? Well, that's 4 out of 52. There are 4 kings in the deck. But now, here's the trick. What's the probability that the second card is a king, given that the first is a king? So if I already know the outcome of the first card, well, then there's only 3 kings remaining. And there's also only 51 cards remaining. So that probability is 3 out of 51. Now what about the and, this third case? The probability that the first card is a king and the second card is a king. It seems reasonable that we would multiply those two probabilities, right? Because the first card needs to be a king. Okay, there's 4 out of 52 chances of that, and maybe, just maybe, that actually happened. So I was successful. And then, if I was successful, then what's the probability that I will be successful for the second draw? And that's 3 out of 51. So it seems reasonable that we take the product of those two, and we do. That's the answer. So it's the probability of E1 times the probability of E2 given that E1 has occurred. Here's another example, and this example is a little bit complicated, but I'll show you the answer, and then maybe we can reason out why the answer works. So in this example, we make a 3-person committee from 8 men, 12 women, and event W is the event that the committee has a woman, and event M, the committee has a man. And of course, we're assuming that this 3-person committee is chosen totally randomly. What's the probability that the committee has a woman? We'll figure that out. And then also we'll look at what's the probability that the committee has a woman given that the committee has a man. And so we'll see that these are two slightly different probabilities. Okay, how about the first one? What's the probability that this committee has a woman? Here's the expression, here's the answer, and maybe we can reason out why it is. So take a look at the numerator. 8 choose 2 times 12 choose 1, 8 choose 1 times 12 choose 2, 8 choose 0 times 12 choose 3. What's going on here is that the committee has to have a woman. So there's either 1 woman or 2 women or 3 women on that committee. And so correspondingly, there's either 2 men, 1 man, or no men on the committee. So the numerator really does express the idea that among these 3 people, at least 1 woman appears. Now, there's another way that you could have done this. So I'll just say as a by the way, we could have made our numerator 20 choose 3, so that's all possible ways of choosing a committee of 3, minus that committee that consists of all men. So 8 choose 3. All right, so that could have been another way that we form our numerator. The denominator, 20 choose 3, is all possible committees, so that would stay the same. All right, so either way you want to think about it, this is the probability that a woman is on the committee. Now, let's tackle the second part. What's the probability that there's a woman on the committee, given that there's a man on the committee? And then we get an expression like this. Look how it's changed. 2 big ideas. First, this third term in the numerator goes away. Because what does this third term represent? This third term is the situation in which there are no men on the committee and there are 3 women. So that does not appear in my new numerator. But also, very importantly, look how the denominator has changed. Since I'm in a situation where there has to be a man on the committee, I'm not dividing by all 20 choose 3 ways. I'm dividing by all those ways that have at least one man. So in fact, I'm subtracting out the possibility that the committee is all women. So there we go. You can see the slight change in the computation for this thing, the regular probability and the conditional probability. All right, here's one for you to try, I promise, much simpler. Take a look at this. Let's suppose that there's a bag that has 8 red marbles labeled 1 through 8, 5 blue marbles labeled 1 through 5, and here are some various probabilities and conditional probabilities for you to work out. Pause the video, give this a try, and then start it up again when you are ready to check your work. Okay, let's take a look. So I'll just slowly show up the answers and see if you got it right. Okay, so there's probability of blue, probability you pull out a red, probability you pull out an even number, even given blue, even given red, blue given even, and red given even. For these conditional probabilities, consider the denominators. In this first case, when I look at what's the probability that I choose an even number given that it's blue, that blue now becomes my new denominator. There are exactly 5 blue marbles, and so I'm now choosing out of 5. So this discussion leads us to theorem 4, the general product rule. If E1 and E2 are any events, not just independent events, but if they are any events, then the probability that E1 and E2 both occur is the probability of E1 times the probability of E2 given E1. Let's go back to the previous example, and let's consider what's the probability that I pull out a marble that is blue and even. Following the rule of the theorem, the probability that it's blue and even should be the probability that it's blue times the probability that it's even, given that it's blue. And the probability that it's blue is 5/13. The probability that it's even, given that it's blue, is 2/5. Multiply them together, and we get 2/13. Now, this is a simple enough problem that you probably could have figured out this 2/13 right from the beginning, because there really are only 2 marbles altogether that are even and blue, right? The 2 and the 4. So we could have done this based on our old ideas of just looking at how many events are satisfied out of the total sample space. But this technique is more powerful and will be useful in many more situations, being able to use the general product rule. Here's another example. Suppose we roll 2 dice. Event 1, at least one die shows a 5. Event 2, the sum of the dice is 8. So check marks. There we go. I'll fill in the 11 outcomes where event 1 is satisfied, and the x's for event 2. Here are the 5 x's, and you can see there's overlap in a couple spaces. The probability of E1 and E2 can actually be computed in a couple different ways. So it actually doesn't really matter whether I start with E1 and then find the probability of E2 given E1, or if I start with E2 and then find the probability of E1 given E2. It should be symmetric, right? Because just the word and, when you look at the original statement, it shouldn't matter whether I say E1 and E2 or whether I say E2 and E1. So let's take a look. How about in this first case? Probability of E1. Do you see what that is? That's 11 out of 36. And then what's the probability of E2 given E1? It's 2 out of 11. And again, I just really want to emphasize this. For the conditional probability, when I'm given E1, that narrows my focus. I'm only looking at the check marks, and there are 11 check marks. And so I have my denominator down there, 11. So of those 11 check marks, 2 of them also have x's. And so that's how we get our 2/11ths for that second fraction. Now, let's do this the other way. The probability of E2 times the probability of E1 given E2. So 5/36, there are 5 x's on the board. Then among those 5 x's, I'm narrowing my focus, only looking at those 5. We see that there are 2 of those that satisfy E1. So 5/36 times 2/5 equals 2/36, and we end up with the same answer in both cases. Let's talk about point number 4, Bernoulli trials, something a little bit different. An experiment might really be the independent repetition of a simpler experiment. We can have experiments built out of experiments. And the simpler experiment, so I don't keep on using the word experiment and getting confused, the simpler one, we call that a trial. Here's an example. Suppose that our experiment is to flip a coin 5 times and record the result as an ordered list of h's and t's. So an example outcome of this experiment might be the list HTTHT. Well, that's the experiment, but really, every single flip of a coin is also itself a little experiment. And you have a certain probability of getting an H and a certain probability of getting a T. So our little experiment, one single flip of a coin, is put together 5 times to make this bigger experiment. So the smaller experiment is called the trial. So every flip of a coin is a trial, and then putting 5 of them together and looking at the outcome, that's the experiment. Well, the thing about these Bernoulli trials and making experiments out of trials is that it's a nice combination of the product rule and the sum rule. So we'll see this. Here's an example. A biased coin has the probability of getting a head as 1/3. Say you flip this coin 5 times and record the result as a list of h's and t's. What's the probability that the outcome is TTTHT? So this is pretty straightforward. The probability of a tail is 2/3, so I get 2/3, 2/3, 2/3. The probability of a head is 1/3 times 1/3 times 2/3. But this is all just multiplication, and multiplication is commutative, so it doesn't really matter the order that I write these in. And so I can write it a little more compactly, 1/3 times 2/3 to the 4th, and there we find the solution. But that same probability also would have happened if I was looking for the probability of, say, T, H, T, T, T. That would also have the same probability. Or H, T, 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 T. That also has the same probability. So it doesn't really matter where that head appears in the list of the tails and heads. As long as I have one head, it will always be the same probability. So we could ask, what is the probability of exactly one head in 5 flips of the coin? We can list out, actually see those 5 different results there. And then we end up with 5 times that one probability, the 1/3 times 2/3 to the 4th. And this is where we really see the combination of the sum and the product rules. The product rule tells me the probability of any one outcome. And then, since these different outcomes are disjoint, I add them together and find the final result. So 5 times the 1/3 times 2/3 to the 4th. Here's a more interesting example. What's the probability of exactly 2 heads in 5 flips of the coin? Again, I could list out all the possible outcomes that have 2 heads. There they are. How many outcomes are there? Well, 2 heads in 5 flips of the coin. I could use the choose function. So how about 5 choose 2? I have 5 spaces. Let's choose 2 of them where the heads will go. So there are 5 choose 2 possible outcomes. You can count them. That's equal to 10. And each outcome has the same probability. So this becomes our expression. 5 choose 2 times 1/3 squared times 2/3 cubed. Here's a final question to challenge you. Give this a try. Show that the probability of getting exactly 4 heads in 11 flips of the coin is approximately 0.2384. See if you can get it. Try your best. All right, so we have talked about conditional probability, and we have talked about Bernoulli trials, and that brings us to the end of section 6.2.